So next talk is by Somaschi, and he will tell us about scaling quantum computation in the light matter hybrid approach.
Right. Good morning. I'm Il, so I will cover that. Sorry. I was also asked to present in general overview of what we do, and representing Quandela, a quantum computing company, I will present many things. I will be overviewing all the activities we perform on the hardware side, on the architecture, error mitigation, error correction, engineering. So I will fly away a bit on these things. So, and usually I apologize because I put equation in my talks. Here I apologize because maybe there are not enough. I will try to keep time for questions, and I will try to also provide answer to questions that I know usually come. But as starting usually, as usually, can we turn off the light? An introduction on the company, which is quantum computing company, was created in 2017 when quantum computing was not hype, so we were quiet doing our own stuff. It was created as a spin-off from the C2N, the Center of Nanoscience Nanotechnology, which is nearby, from a technology that has more than 30 years at CNRS, another French institution, which is nanostructure, quantum dot nanostructure to emit quantum light. And we created, myself, Valérie Angès, and Pascal, the professor, this company to make this device available. And we didn't start with the idea to build quantum computers, but we started with the idea of making technology available for others to build quantum computer based with photons. This is the main idea. We realized then in 2020 that of course it was too slow. The field was advancing very fast, so we internalized competencies, and we are now doing it ourselves. So I will present you what's the underlying technology, what are the approaches in quantum computing, and what we are taking, and also how we build it. Main messages: photonic quantum computing is a very good approach to get there, perfect quantum computers, and there is better ways. Second message, it's very hard, but at least we know how to do it. And therefore, we will try. This is the main team: Professor Pascal, Academy of Science, École Polytechnique, many other things. Valerian, business people, of course. Professor Aspect, Scientific Advisory Board. Before it was a Nobel Prize. So we asked to join, and he joined 2017. And then experts across different fields. Shane is an expert in quantum information and is leading the research team. Jean is an expert in machine learning and software and is leading the product team. And Thomas joined a year ago now, leaving his professorship in Sydney to join and lead the effort in Germany, where we have a subsidiary to do part of the R&D on the hardware. We also have offices a bit around the world, a subsidiary in Canada, UK, and Korea. Now, these numbers are usually very scary for experimentalists, maybe not many of you, but this gives the idea of what we have to build. And we can take two main approaches to build these quantum computers. They're based on matter, they're based on light. And each of them has his own good points and difficult ones for scaling. We like matter-based because we can make one gate after the other. Everything is well defined. We know where they are. We can go back and use them again. But because they are also there, we have to fabricate them. And reaching the millions and more matter qubits, that means a lot of space. There is concern and difficulties in the geometry, where we put them, how we control them, how we fabricate them in a way that when I fabricate 10, I know how to fabricate 1,000, and I know how to fabricate 1,000 more. On the light base, that's cool because the photon, the qubit flies, and we have just to fabricate the objects that generate them, manipulate them, and detect them. And we can also interconnect different processors. So we can build small things, small modules, and make them work together. The problem, though, is that gates are probabilistic. When we do a measurement on a qubit, this is destroyed. And this, it brings headaches to people that want to build these things. So the main two approaches are to make photonic quantum computing universal is with linear optics and with cluster states. The first approach is called KLM from the famous paper in 2001. And it says that we can encode qubits in integrated photonic circuits. If you put it in a path, it's 1. If you put it in the other, it's 0. You use B splitter to create superposition, and you scale it, and you have universal computing. But the people that built it, this model, didn't think that someone would also be crazy to think about doing it. And it turns out that scaling in fabrication is a nightmare because you want to get bigger, the circuit gets much bigger, and you realize that you have very low probability that the photon that comes in the beginning arrives till the end. Later on, a few years later, someone, these people in the paper, mostly Hans Briegel, also in the scientific advisory board, came up with another idea. What about making a huge state of entangled photon, entangled qubit, giant cluster state, and I perform measurement just doing single qubit measurement because the two qubit measurements are probabilistic, and that's giving the headache on the other side. So this came up as well, and is being considered one of the most clean way to do it. But there have been ways optimizing the NBQC original approach, and this is the fusion-based quantum computing approach that was proposed by the company PsiQuantum, where they take the main idea, but they add a trick, which is I perform a correction while I perform my measurement. So if I perform a measurement and it works, I continue doing it. If it's wrong, then I can extract information on how to correct the system. And it starts by generating single photon, making an entangling gate, and having three entangled photon chain. This is an entanglement link, and the ball is a photon. And then I have to create these resource states. So I fuse these 3 blocks. So I fuse them, means 2 photon goes away, and I create a chain, and I create this link, and then I scale this resource state through generators in the hardware point of view, and I fuse them in a network. So a big machine generating this object, many big machines generating many of them, fibers all over the place, and other circuit to do this fusion network. The main ingredient, though, is also the feed-forward technique. It means that when I perform the measurement, I have to be fast enough to modify my circuit to apply to the next fusion operation a specific measurement. How do we build that? What are the error? The error are mostly photon loss. If I lose a photon, qubit is not there and it's gone. So we can understand now how we can build and reach thresholds and how many qubit it means, and we can compute it. So this is a calculation that shows the performance in terms of photon loss, how many photon comes in the beginning, arrive till the end, and how do I reach error correction threshold. And if we compute that protocol into the model, you see that we don't need to reach these millions of qubits, we need to reach 300 to be in that regime. So the idea of, oh, I have to build the millions of photons. Well, no, I can build a million photons, but I reach error correction when I have 300. And it's also very interesting because you can identify the limits of emulator and simulation today, which is around 35 to 40 photons with clusters of GPU. We tried every way, that's the optimal way, and we see where is the limit. So that's how we say, okay, we can build this, looking at the performance, which are engineering challenges, following this curve. We can use trick, of course, error mitigation, and of course, later on, error correction that we build internally. So how do we do in Quandela? We start by using these devices. So this is the object that we are known to do well worldwide, which is a single photon source. We take an artificial atom, it's a nanocrystal, we place it in between two mirrors, we excite it with optical light, we excite the state, and we manage to extract very efficiently each of the emitted photon that the single atom shoots. And that's very important because when we want to build these machines, we have to generate photons very efficiently. And it turns out that if you don't use emitters, you can do it in other probabilistic approach, but you are bounded to efficiencies of 1 to 2%. So in the curve before, if you have to reach very low photon losses and you start with 2%, you start very bad. Basically, you cannot do it. So you have to find a way to find that. And this is a way because this emitter can be pushed in the engineering level to emit at the 99% probability. You have to make the engineering correct. How does it work? That's the single photon source. We need one today to build up to 12 qubits processor. It shoots photon. We use an active machine that demultiplex and routes photon into different outputs. We synchronize them. So the first waits for the last, and then input it in integrated photonic circuits. These white points are active shifter. It means they're used to apply single qubit gate. Here, what we do then is to look at the output distribution. And by looking at what we have at the output, we can track the results. Very important, we don't now encode algorithms in a gate-based approach. We encode it in a photonic way. It means that we transform an Hamiltonian into a unitary matrix that we can imprint in the phases of the circuit, and at the same time, we actively operate all the qubits, which are then all-to-all connected and can provide very high fidelity. So if we measure C0, we can get 99% corrected. If we measure single qubit gate, we can get 99.95 or something. And this is a start to build things. So that's how it looks like. If you want to see more detail, that's the paper. And it's also on the cloud available. So we build a machine, we build the electronic to control all the system. We build an operating system, compiler, transpiler, operating language, open source, it's called Percival, and then the cloud platform, and then a way to code it and play with it. So it's available and it's fun. So we can now test standard benchmarking values, as I said before. It's very important also that we can make it really available. So it stays in a room, no one gets in, it's work 24/7. And we demonstrating we can get to more than 90% availability. So when you now access Amazon, machines there run 99.9 something availability. If you run on Amazon quantum computers, you may find them online 1 day per week, few hours per day, something like that. So if you want to make it business out of it, you have to get to this number. So people will not be very happy. Another important things for calculation, for computing, photons go fast, so we can compute fast. And in algorithms where you have loops like variational quantum Eigen solver, this is crucial because otherwise your computing time extends to weeks or so. And if you pay the clouds, that gets very expensive. So you want to run it faster. And this is another important benchmarking that not all the companies are showing, but it is. Then, of course, we can run emulators. We run it on GPUs, we run it on CPUs. So that's pushing the boundary to the limit of advantage, let's say, and that's the limit of where we can get.
How many photons you need for those 10 qubits? How many encoding qubits?
So we generate millions of photons with this device per second, if we just measure just in front. Then we split them, and we have at the kilohertz rate 10 photons at the output. Most of the time there are 9, there are 2, there are 0, but you get the 10 at 1 kilohertz. Does it answer? So you post-select on the time that you measure the 10. And this is where you get your results. But you run it very fast, so you have not to wait a lot.
Between any.
You can encode gate base into the linear optical circuits in the interferometer. We have developed a way, it's called, is a graphical language tool, and it's automated. So if you write a circuit, then it translates it into a set of linear optical operation, with splitter and phases, etc., etc. So we can make a CNOT that runs with 98% fidelity, correct in any. And it means that the CNOT may take this space, so you have to place another and place another. But the point where I was going after is that we don't really want to play the game of, oh, let's find an algorithm in gate base and map it linear optical circuit. No, we can already find algorithms that we can map it directly and encode them with a linear optical element. So we can access a set of applications which are more performant directly on the photonic language than the gate base. And this is what we are doing in these noisy systems before getting to our correction, where of course you will need proper gate base circuit like. So these are the algorithms we managed to optimize because we see the most performance, and you can already take them in the platform and use them. And that's how the partner work with it. They don't care about learning how it works the photonic computing. Researchers do, and they program it that way. But many others just take these preformed primitives and run it for. This is a list of life science application. Then we have also developed several error mitigation techniques to mitigate the error of the circuit, so fabrication error, which are not error of qubits, they are error of hardware. So we can optimize those so the qubits operation gets with high fidelity. Then we have other two techniques that works on the output of the results, and I'll let you check the paper if you want to know more. But basically saying, okay, if I have my 10 photon at hertz, kilohertz rate, do I have to throw away all the other coincidences when I have less photon? No, I can find a way to extract the correlation even from these lost counts. And that's how we boost the performance, recycling the photon that we thought were lost, but can actually bring information. It's make it very, very simple. But now the interesting part. So how do we get there? How do we scale? It turns out that the single photon source, being an artificial atom, can also host a spin. And if I manipulate the spin, I end up having a matter qubit. The trick is that if I follow this paper, I can manage to entangle this spin, so this qubit, with each of the photons that it was already emitting before. The object turns out in emitting chains of linearly entangled photons directly from the spin, as long as the spin alive. This is the circuit that allows to implement this polarization, encoding, entanglement. That's a sequence, that's a paper. Basically initialize the spin, you make it process, it emits a photon, you reinitialize it again, emits a photon, and you go on and you go on. Right, so now we have this tool. It means that we can do things more efficiently. It also turns out that we can start with spin coherence time, which are so low that no one has ever shown record low coherence time. It means that we can just improve. So we managed to do a 3-part entanglement with just few nanosecond coherence time, but we know we can get to microsecond, which means that we can make very long chain of photons, which are emitted at gigahertz rate. So once again, we can really push entanglement generation very fast to make, at the end, the operation on this qubit very fast. It's also cool because the integrated photonic technology allows you to do gigahertz operation. That's what interconnects and telecom and fibers technology implements. So nothing really new. So now, if we place a spin in the single photon source, it turns out that we have some matter qubit. So at the end, we are not really making photonic quantum computing, but we are making hybrid quantum computing. And then we can choose how much of computing on the photons we can do and how much we can do on the spin. So this paper is the first hybrid spin optical architecture that was developed and was published last year. And it provides the full architecture with error correction using this scheme. And it works as follows. So I have a spin, I make it emit these entangled photons, and then I have another spin, which is identical, emitting again this entangled photon. So now I can use the entangled photon as a way to make these two spins interact at distance, just doing a very simple operation on two photons. And then if I do so, I have 3 modules, and on the hardware side, I have to optimize the photon emission operation and detection on 3 modules and very few components. So my error threshold gets squeezed in very few components. When I do that, then I can just copy paste and put them in a room with a lot of optical fibers and do computation this way. What we perform here as a trick is called a RAS gate, a repeat until success gate, which permits to identify a success, a repeat, or erasure operation on the qubit. So depending where the results on the entanglement operation of the 2 photons, I apply a CZ gate on the spin or a unitary, and then I repeat this with all the spin and all the photon until all get a success, and then I can launch my error correction code and perform universal computation. That's the idea, and that's the tool. So you can see it removes the constraint and the bottlenecks of the matter or the light-based approach. Because in the light base, I lose my qubits when I measure them. Here, my qubit is a matter one, so it's always there. On the matter base, I'm constrained with the number of qubits in the geometry. They have to be close to each other. Here, I can put them wherever they want. They are distant, and therefore, I can look for very efficient codes also for error correction. So it's modular, it's very efficient in terms of resources, it can go at bigger speed, and many other appealing stuff. So in the paper, of course, we do calculation of the error correction. We do it on the photon loss, how much we can allow ourselves to lose photons, and it turns out it's around 2% with this version. Then we extrapolate the ratio of the lifetime and the success gates. And what is cool is coming from this graph that says you just need to repeat this thing an average time of 6 times if you have these losses. So the spin coherence time should be enough to have a chain of entangled photon long enough so I can get the repetition until success that falls in this regime. So as a starting point, it's very, very promising because the thresholds are quite good. So we can start thinking how to build it. Now it turns out that if we compare the approach of generating cluster state with these devices and the spin in the full fusion-based optical approach, then we can extract from the paper that we reduce by a factor of 10 to the 5 the number of components required. I repeat, so for the probabilistic approach, the resources are very inefficient. I have to multiply them, I have to do a network, a technique called multiplexing. So to produce a single photon, a building block with linear optics, and then this, I need 1,200 integrated components, and then another 1,000. So it comes up that one of these resource state generator that for them acts as a logical qubit, it requires 1 million or more of integrated components. And here, because I do it probabilistically, if I do it well with the same performance required, I need roughly 10. That's why we will need less money than them to build this thing. And the machine will also be much, much smaller and much, much less power consuming. Now, this is the work we do on the theory side and on the long term, but we are already building things. We have a factory where we assemble and integrate the quantum computers, that's Somaschi. And we have a pre-industrial manufacturing process, a pilot line at the PVF, so not far from here, where we are scaling the production and the performance of these integrated single photon sources, pin photon sources. And it's the first in the world, so it's the first time that this technology gets out of research lab or research clean room and gets machine, industrial machine, and industrial processes. And then we can scale it. Scale it means simply how many we can fabricate per year. We need to get certain performance, how reproducible it is. So in the full chain of process, we are passing from 500 devices per year to thousands now. And we can scale it even more. Performance-wise, this is the dots of papers or results in the past years, and the missing one are the ones that we have to get to unity, efficiency, and of course, fidelity of the qubits with engineering that improves year by year. Of course, we expect with this pilot line to fulfill what's missing. We also fabricate computers, so we sell them. People buy it, data center buy it, and we ship too. So one thing is sell a quantum computer, one thing is to deliver a quantum computer. So we delivered already two in the past 18 months. We have another one to come. that will be hosted by Gensi, part of the Euro HPC program. A few companies managed to do that. What people do with that? Well, they are discovering quantum computing, they're discovering a lot of fields in industry, related to energy, life science, finance, and mobility. So these are a few people I can mention that are using this code to learn and try to build a path internally to bring quantum computing in their institution and organization. The cloud is accessible. It's there if you want to use it, and that's what basically we do. So we work across all this. So I thank you, and I leave before here.
Quick question for, yeah.
So one question on the last part with the spin. So you use this to still to generate entangled photon at higher frequency, but the quantum information is still stored in the photon, right? Not in the spin.
Yeah, so I went very fast. In the SPOC, spin optical quantum computing architecture, now we use the spin as a computation. But we can use the same approach and run an FBQC architecture. So we can put the cursor on how much we build a photonic quantum computer with some matter qubit, or how much we build a matter-based qubit linked with photon. And the cursor is something we can do. We can play, and the results of the one we choose relates to the amount of resources and engineering effort that we perform. More qubit means more devices, but lower bound on the photonic threshold. More photonic, of course, you need higher efficiency and less hardware devices as a matter. So this is under computing to draw the fastest approach.